Welcome to homework.
In this question, we have two batteries with internal resistance connected in series and in parallel with each other and with an external resistance. And we're going to find the current through each of the batteries and the resistor in all the situations. So first of all, part A wants to know the current in the external resistance in the parallel arrangement. So we're going to need to apply a Kirchhoff's rules analysis to this. I'm going to choose as one of my loops this bottom loop here, where my current is going to flow to the left through the internal resistance of the battery and its potential difference, and then to the right through the external resistor. And my other loop is going to be through the battery pictured at the top down through that internal resistor. So there's my second loop. And then the other key thing that we're going to need to know is applying the junction rule. So we're told that current I is what flows, lowercase I is what flows through the external resistor. I'm going to call, ooh, that's actually not a good color to put there. That's hard to read. I'm going to call I1 the current that goes through this middle branch. And I'm going to call I2 the current that splits off and goes through that top branch. So setting up this junction rule first, we're saying that the current lowercase I splits into I1 and I2. So entering this node here, this junction, I comes in, I1 and I2 are what come out. And now we can set up the loop rule for the bottom loop. So we're going to remember that the loop rule is basically conservation of energy, that the sum of potential rises minus potential drops equals 0. So our only potential rise is 12 volts for the battery. We have a potential drop of current lowercase I times the external resistance. And then we also have a potential drop of current I1 through the internal resistance lowercase r of the battery, which equals 0. And now that top loop is going to look the same. 12 volts for or I should say our outer loop, minus I, little lowercase I times capital R, minus I2 times R, lowercase r, equals 0. So what we can infer from this is that, I mean, we could also, show it algebraically if we needed to. But since the only difference here is I1 and I2, we can infer from this that I1 equals I2, and I'm just going to call it capital I moving forward. So what we can do then is this becomes basically a repeated equation. We only need to complete our analysis with one of them. So 12 minus lowercase I times capital R minus capital I times lowercase r equals 0. We're going to go ahead and put all of the terms with resistance on one side. And now we can substitute the fact that we know capital R. Oh, and actually, yeah. We can substitute the fact that capital R, we know in this case, is 2 times the lowercase r internal resistance. But we can also use our junction rule. So if I is equal to I1 plus I2, and I said that I1 and I2 are equal, I'm just going to call them I, and that means my lowercase I is equal to 2 capital I, and capital I equals lowercase I divided by 2. I just realized I have written some things here that we can erase like that. Okay. So now continuing out with our algebra, we are going to get that 12 equals 2.5 lowercase I times r. When we have a value for our lowercase r, it was 0.2 ohms. So lowercase I equals 12 divided by 2.5 times lowercase r, or 12 divided by 2.5 times 0.2, and I get a current here of 24 amperes. So there's our part A. And part B, we're going to perform this same analysis, but for the bottom figure, which is the series circuit. So I'm going to divide up my screen a little bit like this. This is nice. We only have one loop for this. All right, I'm going to assume that current flows counterclockwise because that's aligned with the potential differences of the battery. So in my series circuit, I have, I'm going to start with the rightmost battery. I have a potential rise of 12 and a potential drop within that battery of minus IR. And then we're going to have another 12 volt rise minus IR, I times little r. And then we have a potential drop through the external resistance of lowercase I times capital R. All of that equals 0. There we go. So this gives me 24 minus 2 lowercase I times lowercase r minus lowercase I times 2 times lowercase r equals 0. So 24 minus 4 times lowercase I times lowercase r equals 0. That tells me that 24 equals 4 times lowercase I times lowercase r. And again, we'll solve this for I and substitute our value for lowercase r, which was 0.2. And I got 30 amperes. Part C asks which one is greater. Well, the series circuit has a greater current. And now we're going to repeat this analysis, but our external resistance will be half of the internal resistance of the battery. What's nice is we've already done so much with this that we don't really have to repeat our analysis. We just have to repeat our substitutions. So part D, repeating the analysis for the parallel connection, which was all of my work in pink before, I'm still going to apply the loop rule and the junction rules in the same way. And I'm going to get to this point of 12 equals lowercase I times capital R plus my capital I current through the batteries, each of the two batteries, times R. But now, instead of substituting 2R, 2 times lowercase r, in for capital R, I'm going to do R over 2. My substitution for capital I is still the same, and I get 12 equals I times R. So I, in this case, equals 12 divided by 0.2, which is 60 amps. And then our, this application of our loop rule, because we didn't have any junctions for the series circuit, our analysis is the same. So we're going to have 24 minus 2 times lowercase I times lowercase r minus lowercase I times capital R equals 0. And now I can go ahead and substitute lowercase r over 2 for capital R. And now I'm going to have 24 minus 2.5 times lowercase I times lowercase r equals 0. So lowercase I equals 24 divided by 2.5 times 0.2. I'm going to get 48 amperes. And between these two for part F, the parallel circuit has a greater current.